Hello, today we're going to talk about Umbral calculus. So at first, an introduction. So about this book written by Stephen Ruman called Advanced Linear Algebra through the Springer website. And I bought it specifically for the section about Umbral calculus because I read some articles about it and I thought it was interesting. So it is a much more elegant way to do some algebra on polynomials. So I will present some definitions, then some examples, and then more definitions, and then an exercise. So at first we'll consider P, the space of polynomials with complex components, so with complex values. And we call P star the algebraic dual. So this represents the dual operator. So if you've did a bit of bracket thingy, Dirac bracket, you know that usually you have something on the right and something on the left. Here, what we study here, this is the space in P, and this is the dual of space P. And it can be a bit weird, but just say that we have two spaces that are linked together. So the bracket LP represents the action of L in the space of dual of polynomials P on the polynomial P of X. So it can be a bit weird definition, but that's the definition that is given. So it's the action in the sense of operator, like a process. So this operator is obviously multilinear. Well, linear and linear. And we will consider the algebra of formal power series. So f, so that the function f of t can be written as a sum with a certain coefficient ak. Now, what's interesting is that you can write this with the bracket by doing the operation with respect to x to the power of k, and you get this coefficient. So this is no surprise if you have worked with such objects before, but it will be useful later. So in particular, f of t bracket x to the power of k is equal to n factorial to the Dirac. So if n is not k, then you will end up with a problem because the spaces will be orthogonal, so it will be 0. If, however, you end up with a power that is the same as the k, then you will have a factorial. Now, if you do the reverse, if you take a unity to the power of k, well, it's the derivative operator t to the power of k, you will end up with p in 0, but not p, the kth derivative of k in 0. This can be seen as a new formulation of the Taylor-Lagrange formula if you apply it here. Now, a functional. So a functional is a linear mapping from a vector space V into its field of scalars. So here we have a functional of L, of the action L, as a variable of t that is just equal to this sum. So once again, a coefficient. Once again, this is no surprise. This is just saying that we can build a functional. And the bracket of a functional is equivalent to this action. So this is a bit tricky, but you can have two ways of writing, either with a functional or with an action. Now, we can build some specific functional, like the epsilon a for a complex coefficient is called the evaluation functional, and it's defined as the bracket of epsilon a with the on the polynomial p of x is just p of x evaluated in a. In particular, if we calculate this function related to the um, action of the polynomial, f of epsilon alpha will be equal to uh, the polynomial evaluated in a, but the polynomial evaluated in n is just t to the kth power. So the polynomial, the operator put something to the kth power will be evaluated in the value a. Therefore, you will end up with a form that is the power series of the exponential, and find the exponential at. Now, this is a bit complicated because when you do that, you have not solved your problem. There are some more useful functionals, like the forward difference functional exponential at minus 1, such that is defined such as that if you apply it on p of x, you get p of a minus p of 0. The Abel functional, that is t times exponential at, that when you apply it in the polynomial p of x, you end up with p prime, so the derivative, applied in a. The invertible functional, 1 over 1 minus t, when you apply it on p of x, you end up with the integral of the p times a decreasing exponential integrated from 0 to plus infinity. The Bernoulli, so it's not called Bernoulli functional, but it has no name and is linked with Bernoulli numbers. So this one makes the integral from 0 to a. And in fact, you can find it back by taking the limit from a going to what am I saying? Okay, so now we'll consider a new notation, t to the power of k, so on the k variable applied to the polynomial p of x represents the kth derivative of the polynomial k with respect to x. So t of k now represents an operator. But by linearity, we can express the operator f as a sum of the polynomial of the operator t of k. So we will have a polynomial of operator that we can just treat as a regular operator or a regular polynomial. So, for example, if you apply a translation operator, exponential at, applied on the xn, it will be equal to x plus a to the power of n, because we will apply a translation. Now, if you apply the forward difference operator, it will do the forward thing, so translation to plus a minus p of a. So this is really useful for numerical methods in which you have to compute the rate derivative. So if you have done a bit of derivative, this should be something that you know about. And other operator that I mentioned here. So the delta series, so we called O of f the smallest exponent of t such that appears with a non-zero coefficient. So for example, the coefficient, the function 1, its first coefficient is of order 0, so O of 1 is just 0. The O of t, its force coefficient is 1 because it's the t to the power of 1. T squared, O of t squared is just 2. You have some nice formula, blah blah blah, and a series with series f with O of f is equal to 1 is called a delta series. So this is very convenient because you don't have a constant term and you don't have some terms that are neglected. And when you have a series, try to find one that relates to a delta series because it's more convenient to do Umbral calculus on it. So for any function f and g that are in the set of formal power series that can be written as a formal power series, you can find a function, a binomial expression, so binomial decomposition, such as this, when you have a product of operator, which is convenient. Now, we're going to talk about an object called Scheffer sequences. So I'm going to read what's on the book. We can now define the principal object of study in the umbral calculus. When referring to a sequence S of n in X in P, we shall always assume that the degree of Sn of X is equal to n. So okay, no problem, it's just a polynomial. It's just a sequence of polynomial. So let f be a delta series, as we've seen earlier, and g be an invertible series, so a function that has an inverse. Consider the geometric sequence g, gf, gf squared, gf to the third, etc. in f. Now, this will represent our sequence. So we will have S0 will be g, S1 will be gf, S2 will be gf squared, etc. And then one can show that there is a unit sequence Sn of x in P satisfying the orthogonality conditions. So I'm not going to go too much in details in what are the orthogonality conditions, but it's just saying that there is only one. So we have two objects, a Scheffer sequence S of n and an ordered pair G of t, F of t. So the umbral calculus mostly is the work to go from an ordered pair to a Scheffer sequence or from a Scheffer sequence to an ordered pair. This can seem really easy, but it's actually quite hard. And the whole point is that Scheffer sequences have really cool properties, and you can study a really high amount of polynomials at once. And once again, so when you do something that is relatively new, like umbral calculus, it's very convenient to have nice objects or nice families of functions. Now, a Scheffer sequence, so may f bar be the compositional inverse of f of t, the exponential of y, so y being the variable, so earlier it was x, times the compositional inverse can be written as such. So that's one of the main formula for the Scheffer sequence, and also another formula that is if and only if, which is not the case here. So if you have remember that here we have a pair, an ordered pair G and F. If you apply this function, you should get this formula, which is very convenient. So all of these formula are very convenient because you have a lot of Scheffer sequences that you actually use, and you can apply all of these to find nice results. So obviously we need examples because now it's a bit unclear. So now we can consider the Scheffer sequence of just the polynomials raised to the power of n. So here here you have the function 1, x, x squared, etc. I think you can find g and f pretty easily. So if you apply the generating function formula, you find that exponential yt is just this, which is not really useful, but it confirms that the formula works, at least for this one. And if you apply a binomial formula, so I did not mention it earlier, but there is also another formula called the binomial formula that applies to Scheffer sequences. You find this one, which is the usually Newton's binomial formula. So it's fine. Yeah, in one step, we found two results that are already known. Now let's try to find some harder ones. So if you consider the sequence of lower factorial polynomials with the forward operator, then if you apply it here, you have this recursive result. And when you apply the generating function formula, so like this on this one, earlier this one, you will find that exponential of y times ln of 1 plus t is equal to this. So compared to earlier, instead of having y to the power of k, we have the lower factorial polynomial. And if you simplify this part, it's equal to 1 plus t to the power of y. Sorry, it's to the power of y, not to the power of k. And you get nice results because you get much simpler relations for your problems. Because if I told you, okay, what's the expansion for 1 plus the derivative operator to the power of y? It's very complicated. You can't do it easily. Now, if you apply the binomial identity, so x plus y lower factorial is equal to this junk. And it's actually one of the formulas for lower factorial polynomials. And also one can find back the van der Waals convolution formula with not of his, but I just say it's left as an exercise for the reader because I'm lazy, but apparently you can find back this formula. Another one would be the Abel polynomials presented here with the functional g of t to be t exponential at. And if you apply it with the formula seen earlier, so the formula was this one. So 1 of g of f bar of t times exponential blah blah blah. If you apply it, then you derivate it, you differentiate it with respect to y, you get this formula. And then when you apply it to y is equal to 0, you get this formula. Now you found the power series development, for the inverse of this operator, t exponential at. So the inverse of this is related to the Lambert W function. But you see that now we are dealing with very complex operators because this is derivative operators times exponential of a constant times a derivative operator. And we are taking the inverse, and the inverse can be expressed like this as a power series. Now, there is also the Hermite polynomial, so I did not remind it the definition. So it's also an Apple sequence, but I'm going to talk about it later. So for the Apple sequence, we don't need the f part, we only need the g, and the g is exponential t squared over 2. And using a property of the Apple sequence, Sn of x is equal to g, the 1 over gt, because it's invertible, times x to the n. when you apply this formula here, you get that hn is equal to exponential minus t squared over 2. And using some other formulas, you find some weird results with very confusing things. Now, the generating function formula, if you apply this to the Hermite polynomials that are Scheffer sequences, you find this result. So once again, we are dealing with very inconvenient operators, but in a nicer way and more elegant. Because if you would have wrote it as a like an operator, you would have very complicated expressions. The Laguerre polynomials are also Scheffer sequences with the function g of t to be this and f of t to be this. Applying the formula, we find this back. And actually, there are like 30 different Scheffer sequences, or almost Scheffer. I'm not going to go too much in detail, but there are lots of functions that are used that are related to the Scheffer sequences. Now, the Appel sequence and the associated sequence. So we'll consider two particular cases of Scheffer sequences. So the first one is called the associated sequence for f of t. So it's a Scheffer sequences was g is equal to 1. So here I did not presented any of the associated sequence, but some of them are and have special properties. But I'm not going to talk about it. And there's another special case is if f is equal to t. It's called an Appel sequence. An Appel sequence for g of t. And I mentioned it earlier, some no other properties apply that are very specific. So we have a Umbral operator. So if we have Sn Scheffer sequence, the linear operator lambda of g of f is defined to be, when you apply to x to the power of n, you just get the Scheffer sequence applied in x. It's called the Scheffer operator. So here I'm just presenting some operators that are used, and I'm not going to explain how it's used because I actually don't know. If P of n is the associated sequence, so once again we are dealing with this case here, we can define a Scheffer operator, so like this one. But since we don't have the information on G, we just call it the Umbral operator of f. So instead of having GF, we just have f. Now, the Umbra Shift. So once again, we have a Scheffer sequence. The operator theta applied to Sn just makes it that you go to Sn plus 1. It's called a Scheffer shift for a certain pair, or for the Scheffer sequence. If P of n is the associated sequence, it's called a Umbral shift. So once again, here we have this special case of a Scheffer shift, was G is equal to 1. Yeah, 1. So now we're going to talk about the agent operator. So if you've done a bit of linear algebra, of quantum physics, things like that, you might have heard of this operator. So it transforms Umbral operator to automorphisms of f, and it transforms Umbral shift to surjective, oops, there's an f here, surjective derivations on f. So one of its properties, for example, if you apply it to the Umbral operator of f over a linear function h, it's equivalent to taking h of the compositional inverse of f. So you can view it as an automorphism, and like it takes the linearity, but it takes the inverse of f. Instead of taking f, it takes the inverse of f. But inverse in the sense, in the compositional term. And it's actually not inverse, it's adjoint. So instead of having this applied on h, you have h applied on this. So you have some kind of double swap. So you swap the order and you swap the f to an f bar. So some properties apply. For example, the derivation. So if you apply it to a Umbra Shift theta, so if you apply the adjoint operator, with the adjoint properties that are very common in quantum physics, you can put this one over here, and you get the Umbral Shift over there. Some other properties apply. So here the Umbral Shift transform to this through the properties mentioned earlier. Well, actually it's a definition, so it's not the properties. And when you apply this, you end up with a nice formula here, and that's just equivalent to k times f to the power of k. Now if we compare both, it's equivalent to multiplying by k, and this represents a derivation. And obviously you can define derivation on umbral calculus. And if you take the adjoint of an umbral shift, it's the derivation of the umbral algebra. So adjoint umbral shift of g is equal to umbral shift of f times the derivative over g of f of t. So an exercise. So I have taken an exercise from the book mentioned earlier, and I wrote a question on the mathematics stack exchange thingy wingy. So it's an article question I wrote yesterday. So this thread is about umbral calculus, and well, I wrote 2 times and an exercise about Apple sequences. So I provide first the question, then the definition, then the first attempt at solving the question, then I ask an optional question if the first method could work, then I propose a second method, and then I ask if my reasoning works to solve the said problem. So the problem is, in the book mentioned, in the chapter about umbral calculus, page 506, there is the following question. Show that a sequence S of n of x is the Apple sequence for g of t if and only if Sn of x is equal to gt minus 1 x to the power of n. So Apple sequence is the particular case of Scheffer sequences for the case in which f is equal to t. And then I checked Wikipedia, of course, to check the Apple sequence. And I have a problem with this. It's that the definition that they give, and the definition given in the first article by Paul-Émile Appel, is actually what they call here a property. And it's very inconvenient for me because the exercise is to prove the definition from a property. So I was a bit lost and I tried to solve it. So I tried to going back to the definitions. So the Scheffer sequence for a pair of the form g of t is called the Apple sequence for g of t. And the Scheffer sequence is defined as I mentioned earlier. I just wrote the orthogonality condition. So here's my work. At first, I noticed that for an exercise, he said that there is this condition that is verified to prove that it's Scheffer. So he uses the orthogonality condition to prove that it's Scheffer. So I assume that this relation proves uniqueness. So I try to replace it with my problem. So here G is just G. Wait, what did I wrote? I think I made a mistake because I think I swapped here G and NK. So never mind. Let's skip this part. I think I'm going to rework on it. So this was the first attempt that I failed, and obviously I did a mistake, so I failed. So I was stuck, and I went back to this page, and I saw a sequence Scheffer, so sequence Scheffer for some invertible series g of t, if and only if f of t times Sn of x is equal to n Sn minus 1 of x. So I thought, yay, that's convenient because we can try to use this way, because if we prove this, then we prove this, and if we prove this, it will also prove the other way around. So one of the optional questions I asked is it possible that this fact is verified, but for Scheffer sequence of non-invertible sequences? So here f of t is equal to t. Yes. So replacing here f of t times Sn is equal to t, and using this the formula that we assume, so we go from right to left. So Sn is not proven to be Scheffer yet. We have to prove that it's Scheffer. So we end up with this, and Sn minus 1 is equal to this. It's just taking the definition. Now, earlier we've seen that T represents the operator of derivation, so it's what I understood of it. However, I'm not sure if I'm allowed to swap the T and the gt minus 1, and which is what I said. Is it equal to gt minus 1 times T of xn? Because I wasn't really sure about if I was allowed to do it. And for me, this tx to the n represents to the partial derivation with respect to x, which would be equal to gt minus 1 times n of x to the power n minus 1, which is exactly equivalent to this. So if my reasoning would be correct, this would solve the exercise. But with my current level in Umbral calculus, I'm not sure that my thing work. And as you can see, I've already done a mistake here. A mistake, yeah, mistake here. Here when I think I swapped G and F here. And you can actually, if you are watching in the future, you can actually come back to this this thing on mathematics stack exchange to see if I did a mistake or not, and check that up. But currently there is no answer if no one took the time to check if I was correct or not. So yeah, thank you for watching. If you have any questions, feel free to ask them in the comments. Bye.